In this video, we are going to explore how forces can be used to increase or decrease the speed of an object, effectively altering its momentum. As we discussed previously, momentum is defined as the product of mass and velocity. For example, if we consider a particle with a mass of 2 kilograms moving at a velocity of 5 meters per second, then its momentum would be the result of multiplying 2 by 5, which gives us 10 kilogram-meters per second. Now, suppose we apply a force to the object in the same direction that it is already moving. This force would cause it to accelerate, meaning it would move faster, and because velocity has increased while mass has stayed constant, the momentum would also increase. So if the same object now moves at 8 meters per second, its new momentum becomes 2 multiplied by 8, which equals 16 kilogram-meters per second. To determine exactly how much force is needed to cause such a change in momentum, we can use the following equation, which tells us that force equals the change in momentum divided by the time over which the change occurs. For instance, if a hand applies this force over a duration of 0.5 seconds, we begin by finding the change in momentum. This would be the final momentum, which is 16, minus the initial momentum, which is 10, giving us a difference of 6 kilogram-meters per second. Dividing this by 0.5 seconds yields a force of 12 newtons, indicating that the hand applied a 12-newton force. An alternative way to express this same formula is by writing the force as the final momentum, represented by mass times final velocity, minus the initial momentum, represented by mass times initial velocity, all divided by time. The final velocity is usually symbolized by the letter V and the initial velocity by the letter U. Let's apply this to another example. Suppose we need to calculate the force necessary to accelerate a 600-gram ball, which is 0.6 kilograms, from a stationary position, meaning 0 meters per second, to a final speed of 14 meters per second, and all of this occurs within a time frame of 0.1 seconds. We start by listing the values. Initial velocity is 0. Final velocity is 14, mass is 0.6 kilograms, and time is 0.1 seconds. Plugging these values into our formula, we calculate 0.6 multiplied by 14, subtract 0.6 multiplied by 0, then divide everything by 0.1. This simplifies to 8.4 minus 0, divided by 0.1, resulting in 84 newtons as the required force. This entire concept becomes critically important in real-life scenarios like car crashes. When a moving car collides with an immovable object such as a brick wall, the momentum of the car and any occupants inside it reduces to 0 almost instantly. This abrupt loss of momentum causes an extremely high force to be applied to the passengers, often leading to severe injuries such as trauma to the head or spine. To minimize these injuries, modern vehicles are designed to prolong the time over which the momentum is lost, thereby reducing the force experienced by the occupants. The key idea is that by stretching out the time it takes to lose momentum, the resulting force becomes smaller. This is why safety features such as crumple zones, seatbelts, and airbags are not just recommended, but legally required in car manufacturing. Crumple zones are areas at the front and back of the vehicle that are designed to deform during a crash, absorbing some of the energy and giving the car more time to come to a stop, instead of halting abruptly. Seatbelts serve two primary purposes. One is to restrain the passengers and prevent them from being ejected from the vehicle, while the other is to slightly stretch, thus lengthening the deceleration time and softening the force applied to the body. Airbags, on the other hand, act like cushions, spreading out the impact over a larger area and longer period by being compressible, unlike the hard surfaces they are meant to protect us from, such as dashboards and steering wheels. This principle is not limited to cars. It also applies to helmets used by cyclists or crash mats used in gymnastics and sports. The unifying theme across all these safety devices is that they increase the time over which the momentum is reduced, which in turn lowers the force on the individual, thereby minimizing the risk of injury. That wraps up this lesson on how forces relate to momentum and why it is crucial in everyday safety considerations. We hope you found it useful and informative, and we'll see you in the next one.